So we can have a formal treatment of defining to finding out whether a state is an entangled state or not, and what is the canonical form of a most general state. Okay, we call it Schmidt decomposition. So in the Schmidt decomposition, let us take state psi, which is sum over ij, alpha ij, psi I, tensor phi j. We have this. Now we have matrix A such that alpha ij is the ijth element of matrix A. Now we will invoke something called singular value decomposition. Singular value decomposition, it states that an arbitrary X matrix of dimension n by m can be written as some U, which is a n by n unitary, some D, which is an n by m generalized diagonal matrix, and V transpose, which is m by m another unitary. So U is unitary, V is unitary. If V is unitary, V transpose is also unitary, and D is a diagonal matrix. But D is a rectangular matrix. What do we mean by a diagonal? So of course there can be two type of diagonals. One is this type of diagonal. Then the diagonal matrix will look like D1, D2, D3, so on, and rest everything is 0. If there is a other type of the long diagonal matrix, the matrix, then we have D1, D2, D3, and everything else is 0. So this is what we mean by generalized diagonal matrix. In another interesting point about the singular value decomposition is the elements D1, the diagonal elements D2, D3, they are all real and they are all positive. They can be 0, but they cannot be negative. They are non-negative numbers. So all the elements in D are non-negative numbers. So this is very important decomposition, and we will be using it in our present treatment. So we have a matrix A, which is D1 by D2 matrix. So we decompose it, we find a singular value decomposition of it, where U, D, V transpose, where U is a D1 dimensional unitary, V is D2 dimensional unitary, and D is the diagonal, generalized diagonal matrix. So Aij, which is alpha ij, can be written as sum over k l u I k d k l v transpose l j. This is how we can decompose element wise matrix multiplication. So the element of the product can be written as the product of elements of the matrices u d v here. dkl we know is a dk and delta kl because D is a diagonal matrix. So we can write alpha ij as sum over kl u ik dk delta kl v transpose lj. It's v transpose lj. So in terms of v, we can write it as jl. So this is the decomposition we get, and we can simplify it by using the delta function. So sum over k u ik v jk and dk. This is how we can write alpha ij in terms of elements of unitary u and v, and the dk is the singular values of matrix A. Now we have expression for psi in terms of alpha ij, and That is sum over ij, alpha ij, psi I, tensor phi j. And we can substitute it here, sum over ij, sum k, u ik, v jk, dk, psi I, tensor phi j. Now let us say we have a vector ek defined as sum over I, u ik, psi I. Psi I is the orthonormal basis in Hilbert, first Hilbert space in HD1. Now what is ELEK? The inner product. That will be sum over I, sum over j, u ik I, L star, u j k, psi I, psi j. I'm just using this expression for EL and EK, and I get this. That will be so this, since psi I is the orthonormal basis, so psi I psi j is a delta function, delta ij. So we can sum over j and replace wherever we have j by I. So we get sum over I, u il star, u ik. And this we can write as sum over I, u dagger, li, u ik. So we are using that u star il is the element u dagger, element of u dagger, li. Okay, this is the identity we have used. Now we have u dagger li times u ik. So the right index and left index matches, and the summation is over that matched index. So it will be a product of the two matrices, u dagger u and the lk element of that. But u is a unitary matrix. This is the condition of the singular value decomposition. So u dagger u is identity. So u dagger u lk element is delta lk. So from here we can see that EL, EK are orthonormal states. Similarly, we can have FK, which is sum over J, U, JK, V, JK, and phi J for HD2. And we can verify again that FL, FK is delta LK. That means it's orthonormal basis. Why did we go through all this trouble to arrive at some expression? Because this expression means psi AB can be written as sum over k, dk, ek, tensor fk, where ek is an orthonormal basis and fk is an orthonormal basis in HD2. And dk's are real and positive, non-negative numbers. Okay, so this decomposition is the canonical representation of the state psi. This is the minimum you can achieve in terms of number of terms. Okay, and this is called Schmidt decomposition. Now you see we have a set of D's. They are the singular values of the coefficient matrix A. Then the number of non-zero decays is same as the rank of matrix A. It means if only the first one or only one decay is non-zero and all other decays are zero, then we have a product state. Then psi can be written as, if we keep d's in the descending order, so the largest one is non-zero and that is equal to 1, so it becomes E1 tensor F1. So from this decomposition we will immediately get the product form of the state psi. But if we have more than one decay non-zero, then the state psi cannot be written in this form. Then the state psi will be, this is when rank is 1, rank of A is 1. When the rank of A is not 1, then psi will be at least E1 tensor F1 with coefficient D1 plus D2 E2 F2 and other terms. So in that case, it is guaranteed that it's not a separable state. So in that way, Schmidt decomposition will give us very quickly will tell us whether a given state is separable or entanglement state. The number of non-zero decays are also called the Schmidt rank. The number of non-zero decays, they are also called Schmidt rank. Now we will discuss operators acting on HD1 tensor HD2, so they belong to the set of operators acting on HD1 HD2. So if T is the operator acting on HD1 and S is the operator acting on HD2, then we represent the operator Z, which is T tensor S. We will define what we mean by tensor here. That will belong to HD1 tensor HD2. So if we apply Z on the state psi, and let us say psi is the product state, then T tensor S, psi tensor phi. So till now there is no correlation, there is nothing here to worry or to consider. So the operator of subsystem A will act on the operator of state of subsystem A, and operator on subsystem B will act on state of subsystem B. So it will be T psi tensor S phi. So this is how the product of the tensor product operators acting on the tensor product state is defined. So now if we have the more general state, which is sum over ij alpha ij psi I tensor phi j. Since the matrix product is linear, then T tensor S acting on psi will be sum over ij alpha ij T psi I tensor S phi j. It will individually on each of the tensor product, it will act in this way. T is the operator on subsystem A, and if we don't apply any operator on subsystem B, that is represented by T tensor identity. Identity means doing nothing on a subsystem. Similarly, identity tensor S will represent the operator acting only on subsystem B, nothing on subsystem A. And these two operators always commute. The operator acting only on subsystem A and operator acting only on subsystem B, they commute. If we have A, operator A, and the elements are A11, A12, A13, A21, A22, and so on. We have a operator with these elements, and if we have another operator with elements B11, B12, B21, B22, and all these elements, then A tensor B is defined as a bigger matrix. So till now we did not mention the dimension of A and B. It can be any dimension. They can be square, they can be rectangular, they can be even vectors. So we have already seen the tensor product with vectors. A11 times B, A12 times B, A13 times B, and so on. A21 times B, A22 times B, A23 times B, and so on and so on. This is how we define the tensor product. We can make some grid here to understand it slightly better. The dimension of this grid is same as this block is same as the dimension of B. So if we write just this block, it will be A11, B11, A12, A11, B12, A11, B13, and so on. A11, B21, A11, B22, A11, B23, and so on and so on. This is just this block. So here we have taken the B matrix and multiply every element with number A1. Similarly, in this block, we have the whole B matrix and multiply the numbers, multiply those elements with A12, and so on. So these lines, these blocks are just to understand, but ultimately we have a much bigger matrix, and the dimension of matrix is defined like this. If A is n by m matrix and B is p by q matrix, then A tensor B will be np by mq matrix. This is how the dimensions multiply. For example, if n is a one-dimensional vector, so it means A is a one-dimensional vector. So if m equals n is n and m is 1, so it's n by 1 matrix, and B is also n by p by 1 matrix. Then A tensor B will also be a vector, and the dimension of it will be np times 1, np by 1. And this example we have seen already when we defined the tensor product of states. So in that way, the definition of tensor product is same for operators and states if we consider states as one-dimensional matrices. Now, if we have A tensor B and we want to find the element Mn here. So, of course, A tensor B is a matrix, and finding Mn element is a very well defined question here. But it will be much more useful notation if instead of mn element, if we say ij kl element. So what we have done is m we are writing as ij and n we are writing as kl. So for example, if our A is a 2 by 2 matrix and B is also a 2 by 2 matrix, then A tensor B is a 4 by 4 matrix. So instead of m going from 1 to 4, m and n both going from 1 to 4, we are saying m is 1 1, 1 2, 2 1 and 2 2. Similarly, n is 1 1, 1 2, 2 1 and 2 2. We are just change the notation from the decimal. We have gone to whatever is the convenient basis here, the ij. So I and j can be from 1 to d1 and 1 to d2 respectively. So you will see in time how this will be a more useful representation for an element. Now we are saying A tensor B ij kl element. So E we can write as, we can open it in some basis, A ij. Okay, let me say ik I k. So we can write matrix A in terms of the computational basis I, which is 0 0 and 1 at the ith place and 0 0 everywhere else. Then k is also like that. So A matrix we can be expanded in terms of the coefficient aik and the basis I, the computational basis. Similarly, B we can define as B JL J outer product L. Okay, let me put a bar here to say that they don't need to be from the same Hilbert space. but we can always find a computational basis in both the vector spaces. Then A tensor B will be sum over, this was summation is over Ik, this summation is over JL. So Ik, JL, all four summations we have here, that will be AIK, IK, tensor BJL, J bar, L bar. We can reorganize the symbols I, J, K, L, A, I, K, B, J, L. They are scalars. They come out on one side. We have I, K, tensor J, L. So we have the operator of subsystem A and the operator of the subsystem B. I should not say A and B to avoid the confusion. But so this we have operator of A and this is the operator of B. This can be written as Ij, Kl, Aik, Bjl, I tensor J and K tensor L, J bar and L bar. So it becomes Ij, Kl. So Aik, Bjl, Ij, Kl, and let us call it eta Ij, Kl, Ij, Kl, sum over Ij and Kl, where we have redefined eta Ij, Kl to be Aik, Bjl. And this is A tensor B, the whole matrix A tensor B. Now, if we compare this with this definition, so we had a computational basis I, J, I, K, and computational basis of B was J, L, and A can be written as I, K, and Aij, K. And this becomes the ikth element from here. Aik is small aik. The ikth element of the matrix A is just aik, the coefficient of I out of product K. Similarly, BJL element is just BJL. So if we compare this representation with this, so here the computational basis is Ij. So this becomes the orthonormal basis in HD1 tensor HD2, and this is the orthonormal basis. So the element what we were looking for, that is A tensor B, Ij, Kl element is actually eta Ij and Kl, because this is the coefficient in the computational basis. And this is nothing but Aik and times Bjl. Just look at the indices. The indices are very important here. The Ij Kl element is not Aij and Bkl. It's Aik and Bjl times Bjl. So there is a small shuffling of the indices here to get the Ij Kl element of the tensor product. This will become very important with time, and when we talk about the positive and non-positive, completely positive maps, when we talk about those things, or the cross operators and super operators, these indices will become very important. One can figure out after doing this thing, it's not very difficult to check that A tensor B times C tensor D is actually A times C tensor B times D. I call it ABCD rule. I don't know if there is a rule or name for this rule, but it is very useful. This we have already used multiple times without us realizing. For example, when we said T tensor S acting on psi tensor phi is T psi tensor S phi, we have actually used this rule precisely. Further, when we said ij tensor ik tensor j bar L bar is equal to I tensor J bar times K tensor L bar. We have used this rule but in reverse. We were given this and we took it to this. So in that way, without us realizing, we have used this rule multiple times. And when we work with tensor product space, this rule will appear multiple times and we will use it without registering it in our mind. So these are the properties of the tensor product of operators. And there is an exercise. This can be fun exercise and slightly involved. If I define a matrix H tensor identity plus identity tensor H, and H is Hermitian. So calculate the unitary, which is exponential of minus I h t over h bar. You can use small u, which is exponential of minus I small h t over h bar. So we have to calculate this in terms of u's, small u's.